Hi, let us today do some numericals on the concept of electric potential energy and electric field. So, firstly let us write the formula for doing all those things. So, formulas. When no external field and when we have field. With potential V only. Okay. So let us write one by one. With one charge, okay. One charge. Q1 or Q. Better I should write Q. Potential energy is equal to QV, and since V is equal to 0, so potential energy 0. But here you have, when you have external field, then you have potential energy. Potential energy is equal to QV. Now when you have two charges, Q1 charge and Q2 charge, when you have two charges, so here you have potential and which is at a distance of R12. This is distance. Distance R12. Okay. So here you have potential energy of the system of charge is equal to Q1 Q2 upon R12. Whereas here you have potential energy is equal to potential energy due to Q1 charge Q1B plus potential energy due to Q2 charge Q2V plus. Now firstly you bring, okay, let me delete this first of all. So at the position of Q2 charge, this Q1 charge will create some potential. Let me write that potential Q1 Q2 upon R12 plus, now in external field we have potential due to Q2 charge and this is a Q2V. So with no field and with field you have potential energy varies. Now suppose you have a system of three charges Q1, Q2, Q3, and so potential energy, and it is equal to, as you know, Q1 Q2 upon R12 plus Q1 Q3 upon R13 plus, now leave Q1, now you do with Q2, so Q2 and one thing Q2 Q1 you have already written, so leaving Q1 you will write with Q2 and Q3, Q2 Q3 upon R23. And when you take Q3, you have added potential energy with Q1 and Q2 separately with 8, so will not add any more term. So this is your potential energy. But when you will do an external field, then potential energy will be potential energy due to Q1 charge plus potential energy due to Q2 charge plus in external field obviously plus potential energy due to Q3 charge and plus this potential. You just simply add this one, K Q1 Q2 upon R12 plus K Q1 Q3 upon R13 plus K Q2 Q3 upon R23. So these things we will be doing. Without external field, we will be using these formulas, and with external field, we will be using these formulas. Now, unit of potential energy. Since we know that potential is equal to potential energy per unit charge, therefore potential energy is equal to potential into charge, therefore SI unit of potential energy is equal to unit for potential volt into unit of charge coulomb. And also, since it is some sort of energy, you can simply write it as joule. So these units you can use, you should use its sub-multiples and multiples of this SI unit, means microjoule, nanojoule or kilojoule or megajoule. These things you will be using. So let's do some numericals. Question number 1. 3 charges minus Q plus capital Q and minus Q are placed at equal distances on a straight line if the potential energy of the system is 0. Find the ratio of capital Q upon small q. So, solution. So let the distances in between the charges be R. So let me show with the help of a diagram only. So you have this as, okay, minus Q charge, here you have a plus capital Q charge which is at a distance R, and again you have a minus Q charge, and net potential energy of the system of charges as given is 0. So let me find potential energy of the system of charge. Since potential energy of the system of charges is equal to K, we will take 1 first of all and we will find potential energy of it due to presence of rest of the charge. So K minus Q into capital Q upon distance in between is R plus K minus Q into minus Q upon distance is, now they are at a distance of 2R. Okay. Now I will take the second charge and then I will find potential of this charge due to presence of the other 2 charges. But I have obtained potential of this second charge capital Q due to this first charge already. So now we will find its potential due to presence of third charge, Q minus Q upon R. So this is the net potential, because the third charge potential is already added while we were doing with first charge and second charge. Okay, so this is a net potential. Now, as per question, according question, this net potential energy is equal to 0. Therefore, in equation, in 1, K minus K Q, capital Q upon R, plus minus minus plus, you have minus and minus comes equal to plus. Okay, K Q square upon 2R, and this is a minus K capital Q small q upon R, and this is equal to 0. Now I remove all the common terms. I'll take common and I'll take to that side. So I'll be getting minus capital Q upon, okay, minus capital Q upon 1. Okay, I am taking common. Let me elaborate this. Okay, let us take K small q upon R as common. So here we get minus capital Q, and here we get plus small q upon 2, and here we get minus capital Q, and this is equal to 0. And now you have minus 2 capital Q plus Q upon 2 is equal to 0, and this implies that small q upon 2 is equal to 2 into capital Q. Therefore, your full capital Q is equal to small q. And you have to find ratio of capital Q to small q. So therefore, changing the side of this small q and 4. So we get that capital Q upon small q is equal to 1 upon 4. Now next question. Two positive point charges of 0.2 microcoulomb and 0.01 microcoulomb are placed 100 cm apart. Now calculate the work done in reducing the distance to 5 cm. So firstly, the charges were at a distance 10 cm. These two charges, 0.2 microcoulomb and 0.01 microcoulomb, and the distance in between is 10 cm. Now you have to bring the two charges close to each other and at a distance of 5 cm only. So, and as you know that change in potential energy, solution, as you know that del PE is equal to work done. And you have to find work done. So, for finding work done, we will be finding potential energies of two positions, and then we will find change in potential energies of the two positions. Therefore, potential energy in one condition, first condition, is equal to K Q1 Q2 upon R. So, firstly you will be changing all the quantities in same system. So I'll be writing, and here K has value 9 into 10 power 9 in SI system. So let me write every quantity in SI system only. Point Q1, 0.2 micro. For micro you will be writing 0.6. And this is your second Q2, which is 0.01 into 10 power minus 6 upon, and R is 10 centimeter, and that is equal to 0.1 meter. Okay, 0.1 meter. This is potential energy 1. Now potential energy in second condition. PE2 is equal to, every charges are same in this condition, only distance has been reduced. So let me write 9 into 10 power 9 into the same charge, 0.2 into 10 power minus 6 into 0.01 into 10 power minus 6 upon, and the distance is changed to 5 centimeter, means 0.05. Now the difference of potential energies. Is equal to final PD, PE final minus PD initial, is equal to PE2 minus PD1, and this is equal to, I'll take every common terms outside, so you have 9 into 10 power 9 into, okay, I'll multiply 2 into 10 power minus 3, okay, 2 into 10 power. I have taken the decimal things in the two charges at the exponent of 10, okay, into 10 power minus 12, and here inside you have 1 upon 0.05 minus 1 upon 0.1. So let us simplify this. So this is your 18 into 10 upon 9 minus 3 minus 12 into 100 upon 5 minus 10, and this is your 20 minus 10, so 10 only. So 18 into 10 power minus 15 plus 9, so this is minus 6 into 10, and this is potential energy, so in Joule only, this is not Joule, this is not Joule. Therefore change in potential energy is equal to 18 into 10 power, 18 into 10 power, okay, let me write this in standard notation. So this is your 8.1 into 10 power, so here we have reduced, so it is your 10 power minus 6, okay. Let me write 10 power minus 1 only. So 10 power plus 1, okay. Here we have reduced value, so power will be added. From 18 it is made 1.8. So here we will be add power. So 10 to power plus 1 into 10 power minus 6 into 10 joule. And this you can simplify as 1.8 into 10 power minus 6 plus 2 joule, and this is equal to 1.8 into 10 power minus 4 joule. And since work is equal to change in potential energy, so this is equal to 1.8 into 10 power minus 4 joule. Next question. Two electrons each moving with a velocity of 10 power 6 meter per second are released towards each other. They are moving towards each other. What will be the closest distance of approach between them? Now, the scenario is that the two electrons are moving along each other. Now, the distance will be closest and they will not move any further when their kinetic energy becomes zero. So it says that the net kinetic energy at that position, at the distance of closest approach, at the closest distance of approach, from which they cannot move any further closer to each other as their kinetic energy is totally consumed. So at that distance of approach, the total kinetic energy must be equal to total potential energy. Now, kinetic energy of one particle is half mv square plus kinetic energy of second particle, second electron also is half mv square into potential energy means k e square upon that r distance. Here we can write that, okay, r the distance of the closest distance. The closest distance. So from here you can find this r, the closest distance of approach. We should take it along one direction. K e square upon r is equal to mv square. That implies that r is equal to k e square upon mv square. Now let us put the values of all these things. For k, which is equal to dielectric force constant, is equal to 9 to 10 power 9 into charge on electron, 1.6 into 10 power minus 19 whole power 2 upon mass of electron, 9.1 into 10 power minus 31 into velocity. Okay, velocity given is 10 power 6 whole square. Now this is the distance of closest approach. So let me simplify this further. 9 into 1.6 into 1.6 into 10 power 9 minus 10 power 9 minus 38, and if you take this exponent 10 power minus 31 in numerator, again you get plus 31, and from here you can get minus 12. Okay, now in denominator you will have 9.1. So on simplifying, you can get, okay, this is your 2.53 into 10 power minus 10. This much meter. Now question B. Question B. How much work is required to separate the two charges infinitely away from each other? when you bring the two charges, then potential energy stored or work done equals minus 0.7 joule. Okay. Now when they are separated to infinite distance, so in bringing them close to each other, you did a work of minus 0.7 joule. So when you separate them to up to infinite distance, the work will be same, but the sign will be opposite. Therefore, when they are separated, then work done is equal to minus of this minus 0.7 joule, and this is equal to your plus 0.7 joule. Now next question number C. So if the two charges are placed in this external electric field, the two charges are placed in some external electric field, then what should be electrostatic potential energy of the configuration? So along with this potential energy that you have obtained in question number 1, this much, you have to add potential energy due to the external field also of the two charges. So the field is given is equal to, here it is given equal to A into 1 upon R square, and since we know that potential is equal to E into D, therefore V comes equal to A upon R square into R. So your V is equal to actually A upon R. So along with that potential you have obtained in question number A, we will be adding V1 due to Q1 and V2 due to Q2 are added in answer of A. Okay, so therefore potential energy in external field is equal to, and your Q1 is equal to 7 microcoulomb 10 power minus 6 into your V, means A upon R1, and another charge is okay, let me write first of all the formula itself. Okay, so this is Q1 V1 plus Q2 V2 and plus K Q1 Q2 upon R12. So this is equal to Q1 is your 7 into 10 power minus 6 into V is equal to A upon R1 plus Q2 is minus 2 into 10 power minus 6 into A upon R2, and plus it is, you have obtained minus 7 minus 0.7. Okay, this is your, let me delete this. Here I have obtained minus 0.7 and this much joule. So let me put the value of A and R, 7 into 10 power minus 6 into your A is your your A is 9 into 10 power 5. 9 into 10 power 5, okay, upon its position. Its position is in centimeter is 9 centimeter along negative x-axis. So I should write as from origin if you are taking. So it will be your 0.09 meter. Okay, 0.09 meter. If you are taking from origin the distances between the two, and you are taking potential energy at origin itself, plus your minus 2 into 10 power minus 6 into 9 into 10 power 5 upon 0.09, and this is your minus 0.7, this much joule. And when you simplify, this is your 7 microcoulomb and this is your minus 2 microcoulomb. Okay, so when you will simplify, you will get 70 minus 20 minus 0.7, and this is equal to 49.3 joule. Okay, now I conclude here. So here at this point, let us take notice of this at this very point. Since electric field depends in this case on location, on position, as it is inversely proportional to square of R, so our potential also depends on its location from origin. So here in first case I have written my 0.09 and it is along negative